we're going to work through some linear correlation hypothesis tests. But before we do, we want to talk about linear correlation, the correlation coefficient. Let me go ahead and grab my pen here. We want to talk about linear correlation, the correlation coefficient R, and what it means to be a linear regression. So there's some examples here in part A about a perfect positive correlation. We say that this has a correlation coefficient of R equals 1, and the perfect negative correlation has an R value, a correlation coefficient of -1. These correlation coefficient values quantify the strength of a linear relationship between two variables. A lot of times the variables are between time and then some other sort of measure, maybe time and temperature or time and profit, something like that. But it could also be between two different variables. You'll notice in the middle, in this no correlation, that there's no relationship. You don't notice them going up as a trend or going down as a trend. So this would be 0 for the correlation. You'll also see the correlation coefficient given as an R squared value. If the value is R squared, that means that it's going to range between 0 and 1 instead. We're going to be using R as our correlation coefficient. Just to give you kind of a quick down and dirty what the correlation coefficient is in terms of a quantity, if I were to draw in a best fit line, that's supposed to be a line and it's supposed to be a pretty decent fit, I can talk about the distance to a point on the line. This is our regression line. Let me write that in. So our best fit line is our regression line. And that regression line minimizes the areas in these squares that I can draw that line up my points with a point on the graph. So essentially I want to minimize the area in each of those squares. As I go to a stronger correlation, you'll notice that those squares are even smaller. I can barely draw them in. And in the perfect correlation, the areas in the squares just don't exist. So those would be equal to 0. There is a big formula. We're not going to worry about that. We are going to be grabbing the correlation coefficient from either the calculator, Google Sheets, or from Desmos. The regression only makes sense if we have a strong correlation. We're going to quantify, this is our goal here, we're going to quantify what this strong positive and strong negative correlation is using our hypothesis test. The nice thing about the hypothesis test is it's the same 5-step test, or for the p-value, the same 4-step test that we've been doing before. Let's go ahead and do our first example. Number 1, is there a linear relationship between the bribe amount you give me and your final grade? We're going to create a scatterplot, and then we're going to conduct a complete hypothesis test at the 0.05 significance level. If there is a correlation, and the regression only makes sense if there is a correlation, then we'll go on to state the regression equation. Okay, so take a look at this chart I've got. If you give me a bribe of $10, I'm only going to guarantee you a 73 out of the class. But if you give me a bribe of $150, I'll guarantee you a score of at least 96 out of the class. We want to start by creating a scatter plot. I have these values in Google Sheets. Here they are. So I've got bribe and grade in Google Sheets. I can go ahead and just drop in a chart, and I can do it here, or I can go to Insert Chart using the Insert menu. So I'm going to go ahead and just drop in a chart. It guessed a line chart, which is not what I want. So I'm going to change this to a scatter plot. There it is. So I changed it to a scatter plot. You can see there's a little bit of an upwards trend there, right? In order to get the equation of this, and it's just not obvious in Google Sheets, Excel would be the same way. I want to switch over to Customize, and then I go to Series. If you scroll down, it gives you the option of a trend line. This is our regression line. I do want it to be linear, so I leave it on linear. And I want to show the R squared value. It will not show me R, but I could just take the square root of R squared to come up with our R value. So if I wanted to come up with our R value, I could go over here and say equals square root SQRT of, what's that, 0.915? 0.915. And then we end up with an R value. The other thing that we're missing here is the equation of the line. So if I go back to, and I can click on these three dots, I want to go back to Edit Chart, back to Customize, back to Series. In those options, I had an, let's see, down, for the label. So I want the label, if I choose the down arrow there, I can use equation. And that gives me the equation of the line. So grade is my y value, so y equals 0.118x plus 74.6. So I also have the regression equation if it turns out to be significant. Okay, that's in Google Sheets. It does a decent job, and you can download data from your homework into something like Google Sheets. But what I really want to do is to put this into Desmos. So I'm going to go ahead and select my data and copy it. I'm going to move over into Desmos, and I'm just going to do a Control V. It recognizes that I've got two columns of data, labeled them Y1 and Y2, and I have a similar looking scatter plot. To come up with the R value, the regression equation, I want to type in Y1, so I'm just typing in a generic line here. So I'm going to type Y1. It automatically subscripts, so Y1 is approximately, where's my approximately? So tilde, mx1, again I just typed 1, it subscripts it for me, plus b. So it gave me the best fit line. It also gave me that same r squared value of 0.9151 and the r value, which was at square root, 0.9566. Remember, that's minimizing the squares that we have for each of the dots lining up to the data values, lining up to the line. We also have the values for m and for b. We're going to use these as we go through a statistics test. So I'm just going to grab this and put this over here to the side, if I can do that. There we go. Let's go ahead and run through and do a statistics test. So number one, we want to start with our hypotheses. Let me grab my black pen. So step number one, I want to start with my hypotheses. So h sub 0, I use rho. That's the Greek letter for r. R is our correlation coefficient. So we're testing rho here. Rho either equals 0 or it doesn't equal 0. Super nice hypotheses. These are the same every single time. If rho is equal to 0, we are looking at a case where there's no significant correlation. If it's significantly different from 0, then we're looking at one of our cases with a strong correlation. So strong or significant correlation. Step number 2 is to find our critical value. So we want to find our critical value, and we're going to do that with table I. Let me go ahead and bring up table I. Here it is, and I'm just going to make it a little bit bigger. So you definitely want to print this off or have access to it. And table I, you'll notice at the top, it gives you the null hypothesis, which is nice. So rho equals 0. The alternative is always not equals every single time for this one. And it also tells you that for degrees of freedom, you want to do n minus 2. We have paired data here, so we want to do n minus 2 instead. So degrees of freedom is equal to n minus 2. We have 1, 2, 3, 4, 5 sets of data. So it's going to be 5 minus 2. Degrees of freedom is 3. I also need our significance level, which is 0.05. Okay, so 0.05, 3 degrees of freedom gives me a critical value of 0.878. This is a two-tailed test, so I do want the plus or minus. So plus or minus 0.878. I'm not going to draw a normal curve to go along with this one since we're testing it with our correlation coefficients. Instead, I'm going to draw that continuum from -1 to 1. These are my values of r. 0 in the middle where we have no correlation. We've just determined what makes a strong correlation. I have to have an r value either bigger than 0.878 or smaller than -0.878, or on the other side. Let's go ahead and highlight those rejection regions. So I've got one here and one here. So I have to be more than 0.878 away from 0. Okay, next we want to find the test value. So we had our r in Desmos. We also found it in Google Sheets, but I'm going to go ahead and use the r value that we came up with from Desmos. So r is equal to 0.9566. That lands well within the rejection region, somewhere around there. So step number 4, we will reject the null hypothesis. If we're going up and thinking about this in terms of a claim and not a claim, let me grab my red pen. We want to know if there's a significant correlation, strong correlation, so that means that my alternative is my claim. We're rejecting the null hypothesis, so we're crossing this one out in favor of the alternative, so that means that we are supporting the claim. So we can use both wordings in step 5. So step 4, we reject. Step 5, we did find a significant or a strong, so a strong positive linear correlation between bribe and grade. We can also say that we support the claim. Because we rejected, we can go on to the last step, which is to state the regression equation. We only state the regression equation if we rejected. So the regression equation is the one that we put into Desmos, y equals mx plus b. Remember, to get this out of Desmos, we typed in y1 tilde mx1 plus b. So we found the values for m and b. So if I put it together, y is equal to m.1176 x plus b plus 74.577. 577. I can also word this in terms of x and y in our variables. X represented bribe, y represented grade. So we could say that the grade, so you can calculate your grade by taking 0.117 times the bribe and then add 74.577. So if you didn't give me any money, this would go away and you'd get a grade of about 74. Okay, so step number 2, or I should say example number 2. So in example number 2, we've got scores for an open note stats exam. Is there a linear correlation between the number of time a student looks at their notes and the exam score? We want to complete or conduct a complete hypothesis test at 0.01, and we're going to state the regression equation if there is a significant correlation. I'm going to do this one with the calculator. So let me go ahead and grab the calculator. We're going to do this one by putting the data into L1 and L2. Before you do that, you want to make sure you have diagnostic on. So I'm going to take just a minute here to show you how to turn diagnostic on. You're going to go second, catalog, and then you're going to arrow down to D for diagnostic. And I'm looking for diagnostic on. Diagnostic on, I hit enter, enter again, and it says done. I need to do this for it to show me my R value. So now that I've got diagnostic on, I won't need to do that again, and I'm ready to go ahead and enter my data. My calculator's set up. Let's go ahead and set up our hypothesis test. Step number 1, null hypothesis, always row equals 0, alternative, always row not equal to 0. So this would be no correlation, and this would be a strong correlation. We can tell which one is the claim. It says, is there a linear correlation? So my claim then turns out to be the alternative. So this would be my claim. Step number 2, let's go ahead and find the critical R value, and we're going to do that in table I again. So we need degrees of freedom. Degrees of freedom is n minus 2, so the number of pairs, 1, 2, 3, 4, 5, 6, 7. So 7 minus 2 is 5, so 5 degrees of freedom. Alpha is 0.01. Go ahead and grab table I. Here it is. And table I, this time we have 0.01, 5 degrees of freedom. So we're going to end up with 0.875. So plus or minus 0.875. Okay, so plus or minus 0.875. I'm going to go ahead and draw that continuum again. I think it's really helpful. -1 to 1. strong negative correlation, strong positive correlation, 0 in the middle, 0.875. So there's negative 0.875 and positive 0.875. I can go ahead and shade in my rejection region. So I just have to be more than 0.875 away from 0. Okay, next let's go ahead and work this in the calculator. So step number 3, we're looking for that test value. I need to go to my stat menu, edit, I want to enter my data in. This works good for small data sets. And I've already entered my data in. So I've got all of my data in. So I can quit here. So second quit, back to stat, and then tests. I'm looking for a linear correlation test. It's towards the bottom. You could also arrow up to find it. There it is, linear regression t-test. So I hit enter. And it wants to know where my values are. So X list is an L1, my Y's are an L2. Leave that frequency at 1, and we always leave the not equal, so rho not equal to 0. I'm not going to store anything in for my regression equation, so I'm going to leave that blank, and then I'll calculate. So we end up with, for our test value, I'm looking for R. It doesn't show up yet. So let's go ahead and arrow down. This is why we turn diagnostic on, so it would give me our R value. So our test R value is that last value of, negative 0.9896. So negative 9896, which lands me over here. So I do end up rejecting step number 4. So I reject the null hypothesis. Step number 5, I did find a strong, this time it's a negative correlation, so a strong negative correlation. I rejected the null hypothesis in favor of the alternative, which happened to be the claim, so I could also say that we support the claim. Because we rejected, I can do one more step, and that's to state the regression equation. My regression equation, if I look over at my calculator, it's written this time in the form of y equals a plus bx. Doesn't matter if your constant term comes first or your x term. They're the same. So I want to make sure I'm just stating it in the right form that matches either my calculator or Desmos or my homework, but truly the order doesn't matter. So y is equal to, I need my a value. Looks like I've got b, but I need to arrow up to find a. A is 107.17, so 107.17 plus b. B is negative, so let me erase that plus. So it's going to be negative 7.877 times x. This is the slope of my line, so it makes sense that I would want that to be negative. If I were to write this in terms of my variables, y is the score, and x is the number of times you looked at your notes. So we could say that our score is equal to 107.17 minus 7.877 multiplied by the times you looked at your notes. I'm going to do this test one more time. I want to do this test using the p-value. We actually have pretty much everything we need from the calculator. But I want to do this with the p-value. I'm going to go ahead and start again with my same hypotheses. Rho equals 0, or rho does not equal 0. Step number 2 now is my p-value. Remember, I'm expecting to reject this one. If I look back up through the results of my hypothesis test in my calculator, p-value showed up right towards the beginning there, and this is 2.119, 2.119 e negative 5. Whenever you have that e negative something, it's a really, really small number. This is the area in the tail cut off by our sample value, by our R for this particular test. So that means that we've got 2.119 times 10 to the negative 5, 5 decimal places, 1, 2, 3, 4, and then one before the 2, 119. This is the area in the tail we're comparing that with that area of, here's my rejection regions, of 0.01. So there's my rejection regions, 0.01 total. We have 0.2219. That would barely fill in anything. These are doubled, so everything's all balanced. Barely fill in anything on either side. So that 0.0000219 fits inside the rejection region, giving us, as we expected, the same conclusion. So this fits in the rejection region. Remember, these are areas in the rejection area because it's smaller than our alpha of 0.01. So our conclusion is the same. So I'm ready for step number 3. We reject the null hypothesis. And step number 4, we have a strong correlation. Okay, so we can do a p-value test, or we can test with the R's. Okay, next example. So for this next one, I'm not going to use my calculator because I'm going to have a big data set. I want to, use the values from our Datability survey to test to see if there's a linear correlation between texts sent and texts received. So as I set this one up, first of all, hypotheses are the same every single time. I don't even need to read my test to put my hypotheses together. I know it's going to be either row equals 0 or row does not equal 0. We're going to do this one using R values. So my next step actually is to find my critical R. So I want R sub C. We're going to use table I. And that means that we need degrees of freedom. And we also need alpha, and alpha is 0.05. To get n, the number of pairs, I need to go to the data. So let's go ahead and grab the data. I'm going to go here to Google Sheets, and let me go back to my data sets. And I'm just going to choose our Datability survey results, which is right here. Now, rather than counting using the row number, instead, I'm going to go over to the data, because not everybody would have filled this out. Let's see, here we go. So here are the number of texts sent. Notice the first person didn't fill it out, and here are the number of texts received, and there are a couple of other missing ones. I already went through this data. There were some words in here. Some people said something like a lot or at least, and I went ahead and took out all of the wording, and I also got rid of some that just said a lot and didn't have a number along with it. So what I want to do is to select all of my data. I'm going to let Desmos tell me how many data pairs I have. So selecting all of my data pairs. Sent are going to be my X's, received are my Y's. That's important. So control copy. Over to Desmos. I'm going to clear what we had for that first example, and I'm just going to do a control V in a blank cell. Okay, so there they are. So I've got a lot of values. I can pick either of these variables to find the length of this data set. If you don't remember your stats functions, you can go to the keypad, click on functions, and then stats, and we're going to use length. So I think Google Sheets uses count. So instead we're going to use length, and I want length of x1, and it will just automatically subscript for me, and we've got 42 data values. Okay, so back to my hypothesis test. 42 is n. So this is going to become 42 minus 2, which is 40. So I need 40 degrees of freedom. Let's go ahead and grab my table. So table I want to scroll down to get to 40. 40. If 40 wasn't in my list, remember I'd always go to the one lower than the number. But 40 was in my set here. I've got alpha equals 0.05, so I'm going to use 0.304. Notice how much smaller these values get the larger your data set is. So 0.304 is going to cut off my rejection regions. Let's go ahead and put that here for step number 2. Plus or minus 0.304. That creates that continuum for us. -1 and 1, 0 in the middle. We've got -0.304 and +0.304. cuts off both of our rejection regions. So we have a rejection region on the left and one on the right. Okay, next, step number 3, we need our test R. We're going to find that with Desmos. So back over to Desmos, here we are. I want to put in my linear regression. So I type in y1. I'm using the variable names from my table. If this was an x2 and a y2, which happens if you have multiple data sets in here, you'd want to make sure and use those variable names. Mine are y1 and x1. So y1 and then tilde, mx1, and it's just subscripting for me, which is nice, plus b. Okay, Desmos is so nice, it just gives me everything I need. There's my R value, 0.937, so I do have a strong correlation. And it also gives me the values of M and B for my regression equation. So let me just shrink this down. And there we go. Oh, I need the R value first, don't I? So let me just arrow up a little bit. There we go. So my test R value from Desmos is 0.937. 0.937 lands over here in my rejection region. So step number 4, I reject the null hypothesis. Step number 5, we wanted to see if there is a linear correlation. So my claim was the alternative. I'm going to cross out my null in favor of the alternative. So yes, there is a significant, this one is positive, linear correlation. We could also say that we support the claim. Because we rejected, I haven't failed to reject any of these because it's not very exciting. If you fail to reject, you stop here. No regression equation. But because I rejected, I can go on and do my regression equation. This is the model that fits the data. So my regression equation, I have it in the form y equals mx plus b. And I can grab my m and my b values from Desmos. There they are. Okay, so I get y equals, whoops, so y equals m, which is 1.0, I'll do 1.09 x plus b plus 2.917. 2.917. Remember, you can also write this in the form, you can swap these, the order doesn't matter. So 2.917 plus 1.09x. Both of those work. You just want to make sure that you're matching whatever your question happens to be asking you. So with my equation, I can also grab the variable meanings. So if I go back to my data, sent represents the x's and y represents received. So sent comes first. Let me go back here to my equation. So this is sent and y is received. So I can say that the texts received is equal to, either one works, right? I'm just going to grab this one because it's second, 2.917 plus 1.09 times the number of texts sent. So we've got a nice meaning for that too, so we can use that regression function.